Greetings and welcome to lecture number 14 on fluid dynamics. The topic laminar flow. This session we are going to discuss the laminar flow between fixed parallel plates. Previous lecture we have discussed laminar flow through a circular pipe. On similar line, we are going to derive the expression of velocity distribution as well as shear stress distribution and the pressure drop when the flow is taking place between fixed parallel plates. So laminar flow between fixed parallel plates. So in this case, consider a laminar flow of fluid between fixed parallel plates separated at a distance b apart, as shown in figure. Now, like laminar flow, here also velocity and shear stress is not uniform across the cross section. For that, we consider a small rectangle fluid element of length dx as a free body. Let the lower face of the element is at a distance y from the lower plate, and here the velocity is v. The upper face, which is at a distance y plus dy from the lower plate, let the velocity be v plus dv. The forces acting on the element are as shown in figure, but for steady uniform flow, there is no acceleration, means the total forces must be equal to 0. So like in laminar flow through circular pipe is concerned, here we are considering, because of the cross section is rectangle, we consider a small rectangle fluid element of size dx dy. The forces acting on this particular element are pressure forces on end faces and the shear forces on lower and bottom face. So these are the normal forces. Pressure force we calculate, that is pressure into area. Area is dy into 1. We consider the width, that is z direction, width is unity. So P into dy. And here the pressure force acting on right face, that is P plus dabba P by dabba x into dx into dy. So this is pressure intensity we can obtain according to Taylor's expression, dy. Then the shear forces acting on bottom face, which is tau into area. Circumferential area is dx into dy, dx into dz. Dz in our case is 1. So tau into dx. And the shear force acting on top face is shear stress is obtained by using Taylor's expression, that is f of y plus f dash of y into dy and into area dx into dz. So these are the 4 forces acting on the fluid element. According to Newton's second law of motion, because this is a dynamic condition, here we can apply the Newton's second law of motion. Summation of all forces equal to mass into acceleration, but under steady conditions, through a constant cross section, total acceleration remains 0. So we can equate all the forces to 0. So these are the forces acting. So these are the pressure forces. Again, as per our sign convention, considering the forces towards right are positive, towards left are negative. So these are the forces P into dy dz, force act on left face, but its direction is positive, minus P plus dabba P by dabba x into dx into dy dz. That force acting in opposite direction, its sign is negative. Then minus into bracket, that is tau into dx. So minus into bracket, tau into dx. So that force is towards left, hence negative. Minus minus plus. So this force is positive into dx dy. So after simplification, we can arrive this particular expression, that is dabba p by dabba x, that is equal to dabba tau by dabba y. Now, in order to develop or derive an expression of tau, we're supposed to integrate this expression with respect to y. But at present, we do not have a finite value of boundary conditions to derive an expression of tau. So we move towards first the velocity distribution. So up to this point, almost the procedure is same as we have done in circular pipe. But here there is a difficulty while obtaining shear stress distribution, that we don't know the fixed limits, finite limits for integration. So we first calculate the velocity distribution. So for that, according to Newton's law of viscosity for laminar flow, we had tau is equal to mu into dabba v by dabba y. Again, remember this expression we can use only when if the flow is laminar. Now we can differentiate this with respect to y. So dabba tau by dabba y, that is equal to mu into dabba 2v by dabba y square. Call this equation number 2. There are two expressions now, dabba tau by dabba y. Equation number 1 and equation number 2. So we can equate both. So dabba p by dabba x, that is equal to mu into dabba 2v by dabba y square. Now here, in order to develop expression of velocity distribution, we have to differentiate this or integrate this expression twice. That is, we take this dabba 2v by dabba y square one side, that is equal to this. Now integrate this equation twice because this is independent on the y direction. So integrating above equation with respect to y, that is dabba v by dabba y, that is equal to 1 upon mu dabba p by dabba x y plus c1. And so, and the second integration we have, that is 1 upon mu dabba p by dabba x into y square by 2 plus c1y plus c2. All this equation number 3. Now the constants of integration we can obtain based on the boundary conditions. And we have for velocity the two boundary conditions. We have at that first boundary condition at y is equal to 0, we have a velocity is equal to 0. So therefore C2 is equal to 0. And the second boundary condition we have at another, that is other end, that is at y is equal to b, velocity is equal to 0 again. So both magnitudes known to us for velocity. That's why we develop first expression for velocity distribution. Unlike shear stress at the boundaries, that is at y is equal to 0 and y is equal to b. Shear stress is maximum, but we don't know what is that expression of maximum. That's why before shear stress, we obtain the expression for velocity distribution, because here the known boundary conditions we know, because at both boundaries, that is bottom boundary that is at y is equal to 0 and top boundary at y is equal to b, at both boundaries velocities are 0, so that we can calculate these constants. So C2 is equal to 0, C1 is equal to this. So boundary conditions means we have to put here y is equal to 0, so we get C2 is equal to 0. Then this form, again we put y is equal to b here and v is equal to 0, we get C1 is equal to this expression. So putting the values of C1 and C2 in equation 3, we have this expression, that is C1 value is this. So this is as it is, plus instead of C1, that is minus d upon twice mu dabba p by dabba x into y. Call this equation number 3. So this again further simplification we can get. We take common, some terms we can take common, that is 1 upon twice mu minus dabba p by dabba x, because already in previous derivation, that is laminar flow through circular pipe, we have discussed that this pressure, this bracket term is always positive. This is negative pressure gradient, we can say. So instead of this, this is nothing but P2, P1 minus P2 by L. So if we take this term common, that is 1 upon twice mu dabba p by dabba x, and minus sign we take common. So here it is by minus y square. So this is the expression of velocity distribution. Now from this expression, again we can say from equation 4, indicates that the velocity distribution curve for laminar flow between fixed parallel plate is parabolic. Like velocity distribution in circular pipe, here also it varies parabolically. So this is the variation of velocity with respect to y. So if we put y is equal to 0, v's are v equal to 0. If we put y is equal to b, then b square minus b square, again this term bracket term is 0, then v is equal to 0. So after putting the boundary condition also we can verify. So the velocity is obviously 0 at the boundaries and it is maximum at the center, like we have discussed in laminar flow circular pipe. So the negative sign indicates that the pressure drops in so this negative sign, that pressure decreases along the direction of flow. Pressure drops along the direction of flow. This is the first part, that is the velocity distribution. Then from this we can derive shear stress distribution. Again, for shear stress distribution, we use the Newton's law of viscosity. According to Newton's law of viscosity, tau is equal to mu into dabba v by dabba y. So instead of v, we can put the local velocity distribution expression. And now we can differentiate the bracket term with respect to y. Now here only this is a variable. So this is b minus 2y. So 1/2 and mu get cancelled. So like previous case, tau is equal to minus into bracket dabba p by dabba y. If I take this 2 inside the bracket, it is d by 2 minus y. So again, from this equation, it is obvious that the shear stress varies linearly with the distance from the boundary. So the maximum shear stress we can derive, that is tau is equal to plus minus. If we put the value of y is equal to 0, we'll get one expression, that is plus b by 2. And y is equal to b, we get minus b by 2. So plus or minus b by 2 into bracket minus dabba p by dabba y. Dabba p by dabba x. This is a printing mistake. It is dabba p by dabba x p by 2. So this is a shear stress distribution across when the laminar flow takes place between a fixed parallel plate. Like the velocity distribution, like in case of circular pipe, both velocity distribution and shear stress distributions are almost orientations are same. So shear stress also varies linearly with P in this case. Only coordinates are different. So it is 0 at the center and the maximum at the wall. So only the magnitudes are different. So this is acting in opposite direction because negative direction. We can say when we put y is equal to b by 2. And if we put y is equal to 0, this is acting towards. So they are opposite to each other. So otherwise, only the directions are different. Otherwise, the variation remains constant. Only just consider this printing mistake. It is minus dabba p by dabba x, not dabba p by dabba y. So this is maximum shear stress, and this is the distribution of shear stress across the cross section when the fully developed flow takes place between fixed parallel planes. Now, in order to calculate mean and maximum velocity from local velocity, so we can substitute y is equal to b by 2 in local velocity expressions for getting the expression of v max. So v max is equal to b square by upon 8 mu. So instead of by minus y square, if we put that, it is b square upon 8 mu bracket minus dabba p by dabba x. All this equation number 5. And the discharge Q for laminar flow per unit width of the plate can be obtained by integrating a small discharge dq passing through a strip dy. So through that strip, if the flow is taking place in the small strip we consider of thickness dy and width, that is unity, then we can integrate that, or in order to calculate the entire discharge through the passage, that is a rectangular passage between fixed parallel plate, we can integrate this expression with respect to b, v dy. So 0 to b. So instead of b, we can substitute this expression. Now, after integration, we have integration of y is y square by 2, y square y cube by 3, and putting the limits of the integration, that is b. So the bracket term we get, that is b cube by 6 6 multiplied by 2 is 12. So we cube by 12 mu in bracket minus dabba p by dabba x. So this is a discharge. So the mean velocity only divided by the area. Area in this case b into 1. So velocity is q upon b into a. So because b into that width is unity, so b into 1. So the expression of v only one b is cancelled. That is b square upon 12 mu bracket minus dabba p by dabba x. So this is the mean velocity. So mean and maximum velocity. Like in previous case also, we have obtained. Now the relation between mean and maximum that we can obtain by equating 5 and 6. So here we'll get the expression v is equal to 2/3 V max. So for laminar flow through a circular pipe, it is 1/2 V max. Here it comes 2/3 V max. This is the derivation of mean velocity in terms of maximum velocity. So this highlighted block expressions you have to memorize for solving numericals. So in order to calculate the pressure drop equation, again from the mean velocity, we can develop expression of pressure gradient. So from mean velocity, if we rearrange the term, minus dabba p by dabba x, that is equal to 12 mu, that is equation number 6. 12 mu v by v square. Again, since the flow is steady and uniform, the pressure drop P1 minus P2 between any two sections 1 and 2 in the direction of flow at distance L apart. So instead of this minus dabba p by dabba x, we can put P1 minus P2 by L, that is equal to 12 mu v by v square. So if we rearrange the term, that is P1 minus P2, that is equal to 12 mu v L by v square. So if HF represents the drop in pressure head, then HF is equal to P1 minus P2 gamma. So 12 mu VL by v square. So this is the head loss due to friction expression if we divide both sides by gamma. But this expression is called as a Poiseuille equation. So like in previous expression, that is expression in case of circular, that is called as Hagen-Poiseuille equation. Here that was 32 mu VL by d square. Here it is 12 mu VL by d square. So these are the expressions only applicable when the laminar flow takes place between any narrow passage, we can say, or between two fixed plates. In case of leakages, sometimes we consider the leakages. So there we consider the two surfaces, and in between two surfaces, there is a leakage takes place. So in order to calculate that leakage also, we consider that two surfaces as a parallel fixed place. So many practical situations we convert into this particular situation, that is fixed parallel plates. So in order to calculate the pressure drop, in order to calculate the discharge velocity, becomes. So that's it from this particular session. At the end of this particular session, you will be derived an expression of velocity and shear stress for laminar flow between fixed parallel plates, and also derive an expression for pressure difference or frictional height for laminar flow between fixed parallel plates. So actually the derivation part is concerned, that is laminar flow through a circular pipeline as well as laminar flow between fixed parallel plates. So the derivations are almost identical. Only thing is that in circular pipe, we have considered a cylindrical element. Here we have considered rectangular element. There the characteristic dimensions, that is small radius, capital radius, small or diameter. Here the characteristic lengths are y or capital D, that is distance between the two surfaces. So these only the dimensional parameters are slightly different. Otherwise, methodology remains same. So this is like buy one get one free. So once you understand the one derivation, that is laminar flow through circular pipe, it won't be difficult to understand this derivation, because on the similar line we have derived. Only thing is that at the beginning we cannot take integration for obtaining the expression of shear stress. because we don't know the boundary conditions, that is at y is equal to 0 and y is equal to D for shear stress. We know that shear stress is maximum at the boundaries, but what is the magnitude of that shear stress, that we don't know. That's why there we can just turn the derivation, that first we develop expression of velocity distribution, and then we have developed the expression of shear stress according to Newton's law of viscosity. Otherwise, the procedure remains same. Uh, that's it from this particular session. Thank you very much.